Hi, welcome to Mechanical Repair. Recently I've had need for a coin cell charger. So some of the little coin cells or button cells that you get are actually rechargeable. They start with either MR or LIR on their number. And I was going to make one, then I discovered really I could buy one for next to nothing. So here is my coin cell charger that I've purchased. It's a CT Young, obviously made in China. And here's its instructions for what use they are. And yeah, it plugs into a normal USB port. It's got 8 slots, 40 milliamps for 4 of them, 20 milliamps for 2 of them, and 70 milliamps for the last ones. Now, I don't really think I'm going to need 70 milliamps. I never charge big coin cells. So I'm thinking I might want to do 2 things. One is to tear this down so we can all have a look and see what ICs they've used, how they've managed to kind of, I think they'll have put things like the inductors and capacitors where these lumps are in the design. But I'd like to see the rest of the circuit, see what ICs they've used and things like that. I think that could be quite interesting. So I'm going to tear this down. The problem being, of course, that this is either a welded or glued. If I can get a start, it will probably come apart. It's indeed glued, but not very well. Okay, cool. That has come apart well enough that I'm going to be able to re-glue it and reassemble it. That's not bad at all, in fact, in terms of the way it's parted company. There's a little bit of untidiness, but you can see that it's literally, I think, it's been glued with little dashes all the way along here. And I think they were CA adhesive and they have given way because they're not that strong on plastic. Let's see if we can get the board out now. I'm kind of hoping this board will literally just sort of pull out. Wiggling, and there we have it. Excellent. And what we can see essentially is they have built a separate circuit for each charger. All those circuits are the same, apart from probably a resistor value. We can see, for example, I'm going to have to get my microscope out so we can see more detail. But this one, for example, is a 20 milliamp circuit. Here is our 20 milliamp circuit, 70 milliamp, 70 milliamp. I would like to convert these two to also be 20 milliamp because that will give me 4 20 milliamp charging sockets. Interestingly, there's very little in the way of inductors or anything like that. That's not so bad because we're only doing step down, of course, from a 5-volt supply to about a 4-volt-ish. And we haven't got much current involved, of course, so all of this is helping. But yeah, these will be a dedicated chip. Let's get the microscope out and take a closer look at what's going on. Okay, so let's take a look at one of our 20 milliamp circuits, and here's our IC. Unfortunately, as we can see, they have pretty thoroughly removed the part number, or they might have painted over it, so I might have to go with a solvent. Anyway, down here we've got a 393, so that's 39k resistor, so I'm pretty sure that will be setting the current limit on that IC. Obviously a dedicated charger IC, and there's not much else on here, to be honest. We've got an LED here. In fact, that's 2 LEDs in one package. So yeah, so that's going to be doing the charging and the standby. And yeah, if we look at the next circuit, we've got the same sort of resistor. But yeah, one resistor, 1 LED or 2 LEDs and a couple of capacitors, and that's all there is for each one of these ICs to set the current, etc. So moving along, there's another one, the same of course. And then we've got our USB with a couple of resistors on that. And then, yeah, we've got another circuit, exactly the same, only this one is coded 18, is that C or D? So I'll have to look up the value for that because that's a different numbering scheme for resistors. So they've mixed and matched their resistor types here. But anyway, it's going to be, I don't know, what is this, 70 milliamp. So it's probably going to be a lower value. 24k here on the 40 milliamp circuits. And yet, same on them all. And look, they are completely identical, just different layout on the board, of course. Anyway, I'm going to try and find a part number and see if I can look at the data sheet. If I can't, I'll have a dig around and see if I can find something that would appear to be the right part on one of the Chinese sites. I completely failed to reveal the IC part number. I've tried scratching it, I've tried putting solvents on, and yeah, not succeeded. But anyway, I thought I'd have a search around for the right footprint on LCSC, which is a Chinese supplier, the type of place that this would be bought from. I looked at the footprint and things like that, And the TP4056, which I've got on here, seems to be about right. If we look at the price, in the sort of quantities that we'd be interested in, 12,000 plus, it is 2.6 cents. So even though you're using 8 of them in each device, then, you know, it's still less than 20 cents. And truthfully, they may well be buying more than this. So there we are. Now, I am actually going to use the datasheet from a slightly more expensive one. I think this one just here. And that's because it's in English. And as you can see, it's the TP4056X. You can see there's not really many more components. So let's just go through what's on here. So the first thing that differs very fractionally is that on the VCC line, there's a 0.2 ohm resistor up here. That doesn't appear on the board. Its main job really is when we've got a fair amount of current going through the TP4056X, we use that 0.2 ohm, or you could even go a bit higher. It dissipates a little bit of the energy that's being dropped by the chip. So in other words, we're just losing a little bit of voltage in there instead of in the IC. That means we don't have to dissipate heat from the transistors in that IC. So that's all that's for. And of course, they've just missed that out because we're not going above 70 milliamps, are we? So moving along and looking at the next component, it's a 10 microfarad capacitor, and there's a 10 microfarad capacitor on the output as well. So one here and one here. So the TP4056 is linear. It's essentially a lot of op amps in feedback configuration and also comparators. And on the output is a MOSFET. So decoupling of the power supply is very important, hence the first capacitor. And we also do need some smoothing on that output as well. Now there is a 1K resistor here. And that is actually just for the LEDs, to limit the current through the LEDs or drop the voltage for the LEDs. We've got 5 volts up here and we're dropping the voltage, but that isn't needed, of course, if we use 5 volt LEDs. After that, we've just got our prog down here. So this is the resistor that we pick in order to control the maximum amount of current that's delivered into our battery up here. And that's it. There's nothing else on here. There is some discussion here on how the current setting actually works, and we can see that we can do a fairly simple calculation to actually find out that current. Of note, when we're charging in constant current mode, this V prog on the top line, that's a 1, programming using 1 volt. And that means this simplifies to IBAT equals 1100 divided by R prog. Now I think actually looking at the values of the resistors in the device that we're looking at, that the number for this particular IC that they've chosen isn't 1100, it's probably a little bit higher than that. But it's going to be in that ballpark. So I'd be a little bit remiss not to mention that this does have temperature sensing as part of its circuitry. Just here, this is the temperature sensing part. So there's an NTC which can be attached to the battery, and then we've got a resistive divider to set a threshold essentially, and a smoothing capacitor, and that connects to the temp pin. But if you don't want to do that, and we don't in this case, because how would you attach it to your coin cell, then you can just leave that pin floating. And that's exactly what they've done. That's also shown on that demo board that we looked at a moment ago. Temp is just taken to ground and boom, there we go. And it just decides at that point that it's in range. And it's always in range. Of course, if we're dealing with small currents like 20 milliamps and things, then we're probably not going to overheat our battery. Of course, if we take a very small battery and put it in, let's say the 70 milliamp, then there's a bit more risk. But anyway, I don't think we're going to have a huge amount of trouble from that. So what I'm doing now is connecting one 40 milliamp output to my programmable load, and I'm going to gradually up the current that I'm demanding. And we should see the red light is on to show that we're in actual charging mode at the moment. But anyway, that way I'm going to find out the exact current limit of each of the ports. Now, from that, I can just verify or adjust the programming formula that we saw in the datasheet. Essentially, I'm just going to rearrange that formula that we saw, and I'm going to plug in the numbers. Since I know the resistors on the board are 15K for 70 milliamp, 24K for 40 milliamp, and 39K for 20 milliamp. So easy just to plug in. So once I've got that, I can then work out what resistor I need for a 10 milliamp port, because I don't really need the 70 milliamps. I'd rather switch them across and make them 10 milliamp so I can charge very small cells. So just waiting for this to cut out. I'm approaching 48 milliamps on the front. There it is, it's gone. So 48 milliamps on the 40 milliamp port, so a bit higher than it should be. Now I'm going to repeat this with the other types of ports just to get some more readings. I'll put them all in a spreadsheet and show you what I've got. Here we have it then. Now keep in mind that I'm using 1 milliamp steps on my programmable load, and it's got about plus minus 1 milliamp of accuracy, so there can be about 5 or even a little bit more error on these readings, but they're good enough. So in summary, the 20 milliamp was quite a bit over at 29 milliamps, but the value of the program formula when we work it through comes out almost as on the datasheet. 40 milliamp came out at 48. Again, that's pretty close to the datasheet, but 70 milliamps was 81 milliamps. So that's less error, but the value compared to the datasheet programming sort of factor was quite a bit further off. So what I've done is I've taken an average of 1166, I've applied the datasheet formula to find my resistor for 10 milliamp, and it reckons it should be 117k. Now, based on the fact that the lower currents do actually seem to have a programming factor closer to 1100, I'm actually going to make it 110k, not 117k. I'd rather have that little bit more headroom on the current rather than cutting it too short. So I'm going to give it a go. So I put on the 110k resistor, but it was coming up just a bit short on the current, just 9 milliamp instead of 10. So I've reduced it down to 100k. I'm tacking that on and I'm going to give it a go. Now I also happen to spot a problem with the standby and charging LEDs when I put the resistor on, and I'll look at that with you in a moment. With the 100k I am delivering the desired 10 milliamps, but notice that the charging lights are on when it should be in standby. So how can that be when there's actually no current flowing? There's no battery in here. So time to dig deeper into the datasheet. So here's our little simplified diagram of the actual IC. And we're very interested in this area down here, which is our prog. And we can see that the top of our prog is sourced by a 3 microamp current source with a maximum compliance voltage of VCC. So 3 microamps over 100k is going to give us 0.3 volts. So just here on the input to this comparator, we've got 0.3 volts. Now, if we look what's connected to the other side of that comparator, C2 here, then we can see it's connected to 0.1 volts. So here is the 0.1 volt and the 1 volt that we talked about earlier when we were looking at the data sheet. And we can see that there's a battery controlled switch. So in other words, it's switching between pre-charge and charging, depending whether there's a battery connected, and that's going into this here, which is the current amplifier. But we're not going up that far because we're just in this piece of comparative stuff down here. So we've got 0.3 volts on the input to this comparator, 0.1 on the positive. So the output is going to go down to ground. I can't draw that, but anyway. The output is going to go down to ground, so it's a 0 on the input to this NAND gate just here. So we're going to have 5 volts here driving this MOSFET, driving the MOSFET, and actually pulling the charge down to ground. So our charge LED is going to light up, and that's all. That's why it's lighting up. And of course, because this output is low, then if we go to the standby, then that MOSFET isn't switched on and doesn't therefore conduct to ground. So we're done with that. That's our standby off, our charge on, even though the upper half of this circuit isn't actually delivering any current to the battery. So I'm just kind of, I've just cleared this off so we can kind of look at one or two other things. I've been scouring this datasheet to see if it specifies the lowest amount of current it can provide. I've managed to find a couple of graphs. So there's one just here, and that actually is unspecified below 50 milliamps. Now we know we're getting away with 20 milliamps. The other thing I was wondering is how good is that iProg thing that we've just been looking at? What's the current program current should be 3 microamps according to the diagram, But on this page, it shows it as 2 microamps typical. So clearly they're not all that tight with that specification on this 3 microamps on this diagram just here. Because one of the things that I think about is, well, how did the 39K work then? Because at 3 microamps, 39K would also be over 0.1 volts. But if it's only 2 microamps, then 39K is not going to be over 0.1 volts. So I think that explains it. We've really only got about 2 microamps here, not 3 microamps. And 39K isn't triggering. We're probably okay all the way up to 50K, at which point the charge light will light up. But at 100K, whether it's 2 microamps or what, we don't stand a chance, unfortunately. So there we go. That's our problem. There's nothing we can do about that charge. Hopefully, I think still, looking at the rest of the diagram, I think the actual charging will take place as intended. So at this point, it seems to be working with 10 milliamps. And I've decided to reassemble it. So I'm actually just gluing this with super glue or CA glue, whatever you want to call it. And I'm using an activator on the other side. Unfortunately, I have managed to get a little bit on my fingers. So it's all back together. I definitely need to do a bit more cleaning because I got quite a lot of excess super glue on the sides. But it's all together now, it's working. I've labelled it so I don't forget the modifications. It came apart easier than I expected, although it was glued shut. It's a really simple circuit. In fact, it's probably as simple as you can get. But it was fun to take apart and explore and track down the IC, of course. I did spend a bit of time checking the charging currents, which are really not very accurate at all, and also figuring out the values for my own 10 milliamp modification. That, of course, led to discovering that the charge and standby indication won't really work properly below a set current of about 20 milliamps. Anyway, it's all back together now, so I hope you enjoyed that little teardown and mod. If you did, please don't forget to like, subscribe, leave comments and share. Anyway, see you soon. Bye for now.